Hey guys, welcome back. And today we are doing this system design online payment service. So let me start with a little thought experiment. And like you go out for dinner, right, with five friends, and your bill arrives. Now there's a chaos. Like someone opens Google Pay, someone opens Phone Pay, someone opens their Visa, and all those things. And one guy wants to settle later. That guy, we all know that guy, right? But here's the fascinating thing. When you actually tap pay, something extraordinary happens in the under 2 seconds. Your bank is called, a fraud check has been run, the balance update across multiple accounts, a confirmation notification fires, and the restaurant systems settles it the next morning. That's invisible infrastructure, right? That's what we are building today. So I am Vivek, and this is a complete staff level engineer system design breakdown of an online payment service. Think like PayPal, GPay, Razorpay, like those things. We are going to cover functional requirements, non-functional requirements, API design, high-level architecture, and a proper deep dive into the hard parts. So take your coffee and let's go. So now let me give you a detailed thing that what we'll be doing today. So we will be building a digital wallet platform where users can send the money, right? They can pay the merchants, and at checkout they can withdraw from their bank account. Yeah, and we needs to do all those things into a secure sitting layer, right? And we are not building like Visa or MasterCard. We are not building a bank infrastructure. We are building what? We are building the application layer, right? So basically, we are building accounts, we are building wallets, we are building transactions, we are building fraud detection, we are building currency conversion. So how it will look like on a very small case, it will look like this. There will be a user, okay, and then there will be a platform, and then there will be a bank. So this is like user, and then a payment platform, right? And then there will be a bank or basically a external processor. So it will look like something like this. And we can go with this way and this way. So don't worry, this is not a problem solution. We are just trying to build it, right? So now in a real interview, this is where you will pause and clarify the scope, right? This is like a basic structure of the interview. Online payment service, user will have a payment platform, and then you will do all the things with the external processor. So here you have to pause. You have to then ask like, what are we supporting, right? Are we supporting what? We are supporting credit or debit. Card payments are we supporting? Or are we supporting only wallet to wallet? So this is a single answer which can actually uh, double your design complexity if you don't get it. So confirm it early. So for today, we are supporting both because it's a interview. It's not an interview, right? It's a session. So we are supporting both. By both, I means we are supporting wallet to wallet as well as we are supporting the credit and debit and card payments. So, and how we are supporting. So this external processor, which we talked about, it will be via Stripe or like Aiden. So basically, if you just know Stripe, it will be good, right? So what are the credit debit card payments? What are the wallet to wallet things? Let's talk about this. So in order to do talk about all those things, what we need to do? We need to first clarify the functional and non functional requirements, right? So let's talk about I would like to structure the functional requirements. It's a very simple thing. Like I would like to structure the functional requirements by actor, like who does what. So for a payment system, we have three actors, right? The sender, that means the payer, and second is the receiver, that means either the merchant or an individual, right? Or like a platform itself. I mean, you kind of paying it to maybe Amazon or something. So, and I will tag each requirement as P1, P2, P3. P1 is a must have, P2 is should have, and P3 is nice to have. So, in an interview, this will signal that you can prioritize. You can actually, you're not just listing features, you can think like a PM too. So let's talk about sender or payer kind of a functional requirement. So first is that it's a P1. So let's talk about P1s right now. It can register and it can verify the identity. Okay, so how you can register and verify? You can have an email, you can have a phone, or you can have a KYC document also, or no, I mean, it has everything. Now, again, the second P1 will be you can link payment methods like your bank account, right? Your debit or your credit card. Now, again, another one will be you can send money, right? You can send money via email or ID. Then you can also split a payment. The It's a good one, but it's a P2, right? It's a payment. So this one will go to, I think, P2 because anyways, like splitting something is like not so like what another P1 can be. You can pay a merchant at checkout, right? So like via suppose in-app redirects or payment link. So now let's talk about another P2 is like you can schedule payments like subscriptions and rent. See, this will be very but beneficial when we talk about scheduled payments because it will come into all those things. So let's not worry about it. Let's just focus on the requirement gathering. You can request money from someone, right? Like the way we do in Revolut if you are watching from India or Europe, right? Then on the receiver side, like on a merchant side, what you can do, what can be their, you can say, what can be their priority ones. The P ones should be, you can receive the payment, right? Payments and see them credited in the wallet. And another one is you can withdraw the wallet balance to a linked bank account. So you can also have T+1, which is standard, or you can have like an instant for a fee. Now the P2 will be you can issue full or partial refunds, or you can generate payment links or like QR codes, right, for offline things. Now, what will be the for platform? For platform, the P1 is like platform is like for you. So what you will do, you will have a real-time fraud detection, right? How you can do, you can flag, yeah, you can also block the suspicious transaction. You can have like a multi-currency support like live forex rate, right? You can also have another P1 called full transaction history because that's what we wanted to do. And it is like with receipts, status updates, or filtering. Now, what are the P2s? P2s can be your buyer and seller protection. What is the protection? I mean, that means you can charge back handling, dispute, dispute resolution, right? And then there is like notifications via email and such. So this will be your functional requirements. This is a for like good set for us, but critically we are going to the scope today's design on the P1 side of it, and we will reference P2 where it's architecturally very interesting for us. But we won't over engineer for features. Like so, this is a real signal for interview lovers. Scoping down everything and then telling like I will pick the right subset and go. Then we can go deep into it. Okay. So now let's come back to our thing called uh, another one. Uh, what do we call it? We call it NFRs. So before I list the NFRs, I need the anchor numbers. What are the anchor numbers? You need to write these numbers large on the whiteboard because they'll anchor every decision you make. So before I hit NFRs, right? Like what are these? Suppose you assume 50 million, it's your daily active users, and you are getting two transaction average users like per user, two transactions uh, per day. That means it's around 100 million transactions, right? Per day. Now you have to get a rough estimate on per second how much you can do. You can actually divide it by 86400 to get it like that, or generally you can also divide it around to like 100, like 10K, 100K, right? Not 100K. Yeah, I'm like 100. 10K. So it will be 10,000, 100K. Okay. And now you do this thing. So you can divide it out. So basically, with if you do it by 86,000, you will get like 110, sorry, 1 lakh uh, around something. But what you will do is, sorry, but you can take around 1,000 transactions per second. So that means what? It's a normal average. But when the payments are spiky on the peak, what you will do? You need to take around, like you can ask your interviewer, but you can take either 5x or 10x like that. So let us take 10x. So you will take around 1,000 transactions, uh, 10,000 transactions per second. Okay, and right now we have to do this. We have to do this. So now what happens? Now your big five NFRs comes into picture. The first thing is like strong consistency, right? Over availability. Why did I say that? This is the most important architectural decision you have to make because in most distributed systems, you will follow the CAP theorem and lean towards availability. If two nodes disagree, you will still keep serving the traffic. But in payment system, we will flip this. Money must never be double charged. Write it down. Money must never be double charged, right? So that means it must never disappear. A temporarily unavailable payment is a bad user experience. A double charge is a fraud incident, a legal liability, and a customer service nightmare. So we accept a slightly higher latency and occasional unavailability in exchange for correctness. So correctness means acid transactions in the on the ledger, right? On the ledger. So always remember this. So basically for the payments, you will go with ACID. So consistency will beat availability for payments every time. There is one trade-off you must state explicitly in the interview, and that is this one. Now, the second one we will take care of is idempotency. See, the most important word in payment engineering is this. So raise your hand. Right now, think about a scenario when you have ever tapped the pay button twice and because the loading was spinning and it was taking so much time. So idempotency means no matter how many times you make the same request, the result is always the same. You will only get charged once. You will only do exactly once. We do this by requiring every payment request to include a idempotency key. Basically, what is the idempotency key? It's a unique ID that the client will generate, and if the server see the same key twice, it will return the cache results from the first call. No second charge. This is the most important correctness guarantee in payment engineering. Without it, any network hiccup becomes a billing disaster. So how it will be? So basically your idempotency key will look like this. It will be having a UUID version 4 and the server will check the Redis and it will say found. So it will return the cache uh, response and then you can process and store. Now let's talk about the third hero of the scenario is called avail high availability. See, we are going with high availability. Skip the like you can say you let me just give you the clarity. Otherwise, you will bite me on this that you are not writing spellings correctly. But I think you are able to understand what I'm saying. Or okay, so 99.99% availability means what? That means you can only have 52 minutes of downtime per year, right? So it's very sound generous, but it's not. Achieving it requires a multi-region deployment, circuit breakers, every downstream call, graceful degradation is very important and very interesting in fraud system. So if a fraud engine goes down, we don't block all the payments. Instead, what we will do is we will allow low value transactions through, like suppose $50, but we will flag them for async review. But high value transaction will still get blocked. So what is there? Uh, Graceful degradation, right? So allow low value transaction, flag them for async review, block high value. Okay, I'll come to the diagram, but for now, we just go to this. Now we'll talk about security and compliance. Why it is coming here? See, for card data, we need you to have the PCI DSS compliance. That means your payment card industry security compliance. This means like all the raw card numbers, your SSNs will never be touched from the application servers. What you will do is you will tokenize them through a payment processor immediately, and the token will live in your DB, and all this data will be encrypted via AES 256 and it will transit via TLS, right, 1.3. These are numbers. So even if you are serving European users, you need 3D secure. Okay, and then there is a OTP also in the card payment, right? Now there is another thing which is called GDPR. Like user must have a right to erase. You cannot delete financial transaction records. So how can do a delete? So there is a legal requirement to keep them for 7 years. The solution is you don't delete, right? You don't delete it. You anonymize it. Basically, you remove the user reference from the hash and you can convert it into a hash. That means the transaction is remains, but the personal incident identifier is gone. Okay, now let's go to the last one, which is observability and auditability. So why it is required? Because every transaction will have a correlation ID. It will trace the from end to end across every service it touches. So every state change in the ledger must be logged. What change, when change, it's changed, who triggered it, and why. The ledger must only be append only. That means there is no update, no delete, right? Every reversal or correction is a new row. This will let you replay the history, reconstruct any wallet balances at any point of time. It's very essential so that you can have it in your data, in your system to kind of analyze in case anything comes back. It's essentially a event store for you. Every night a day you will run a reconciliation job which will compare the ledger against the bank statement, and a mismatch will trigger the alert. So now let us come to high level. No, no, I'm sorry. I will take more time. We will design some APIs. Okay. So, what design you will take? So, let us use REST. Okay. Every mutating request like post, put, patch, we will have a item potency key handler. Okay. And it will be in the header. Authentication we can have with OAuth with short-lived JWTs, 50-minute expiry plus a refresh token valid for 7 days. So let's walk through the core things. So let us just talk about the first thing, which is like uh, like a post, right? Post will be what? Post will be like you can have version one, you can have users, and then you can have register. And what it will have, it will have a body will have their email, phone number, okay, and country and the currency. Now what you will send, it will response will be you will send the ID of the user, the wallet ID of the user, because you will create a wallet, right? And the status as KYC pending. Good enough. So two things to notice here. Registration will immediately create a wallet. This is tightly coupled to account creation so that your user sees, yes, I am in. Second, the status is pending KYC. The user can't send the money yet. You have to verify it. So KYC is kicked off asynchronously and will not block it. Everything will happen. He will get a mail. He has to upload and all those things. But he can still use the system. Now let us talk about get, where we one will say one of the things is wallets, and you will have a wallet ID, right? And you can have like balances will have currency, it will have available and pending, all the things. Then they will be like different. So it will be like this, it will be a array of currency objects of currencies objects, like you can have multiple object, right? And you can also have like updated it. Good thing. So kind of understood. Notice available versus pending. So available is what you can spend right now, and pending is reserved, like it has been deducted but not come yet, and all those things, right? Now let us talk about this is done with the users. Let's talk about payments. Okay, payments is like post. You will have V1, you will have payments. It will like initiate a payment and all those things. Now in the header, you will have an item potency key, which is a client generated UUID. Then you will have the payload, or like this, you will get sender uh, wallet ID, you will have receiver wallet ID, right? And you will have amount, you will have currency, you will have description, you will have payment method. The payment method you can have in enum, that's fine. Now you will have a response that you have a payment ID. Okay, payment ID. You have the status as processing, and you have like estimated completion. You can have this, like that's fine. So two very intentional choice we have made here. One is that we have returned 202 accepted, right? So what we have done is will return 202 accepted instead of what? Instead of 200 okay, because payments are async. So we accepted your request, but we have not finished processing it. That means if You return 200, it will say that we have completed your request. So two, the client can retry with the same idempotency key if the request timeout. The server check Redis if the key is there, and it will return the same 202 without charging. That's the magic. Now we talk about another thing called get v1 payments, and we will have the ID here, and it will give us the same thing. So this is a polling, right? So we are getting the payment. So the same thing, it will have payment ID, it will have status, it will have amount, it will have currency, it will have fees, and it will have completed at. If not, status will be processing and completed at will be blocked. So there are certain things, right? You will have like processing, completed, fail, reverse. This client will poll this, or better, what is this? You will listen to a webhook. So either you can poll it or webhook or polling. Okay. Now let's talk about another one. We will have a V1 of payments, right? You can have ID and you can have a refund. Okay, so you can have this as well. So payment partial refunds are supported. So key thing here is a refund does not update the original transaction row. It will create a new ledger entry and carry it back to the buyer. So the original is always immutable. Now let's talk about the last thing before we go to a high level design is we have literally touched this. So like this, why a webhook? Because polling is rude, man. Rather than making the clients poll every second, we push events to them. So merchant will register. So what will do? Merchant will register a webhook URL and the events they care about, right? So we can deliver at least once with exponential backoff on failures. तो एक्सपोनेंशियल बैक ऑफ ऑन फेलियर्स राइट जब तक प्रोसेसिंग में है तो ठीक है sorry so whenever it's in processing it's okay sometimes I switch to Hindi it's the first time and it will be last time for sure now every webhook payload will be what so how it is very easy right anyone can actually now trigger hook the webhook how will you actually now preserve security so there is a thing called signature here so it's actually a hmac um, SHA-256 secret signature, and this receiver will validate the signature before processing. This prevents replay attacks, spoofed events, right? So since we deliver at least once, the merchant handler must be idempotent too. Yes, idempotency appears everywhere in the payment system. So हमको at least once करना है तो भाई अगले बार भी so there is like those things also needs to be taken care of that they need to get that idempotency check there itself. Did we process it? If yes, then we don't need to. We just need to give the previous one. Now, my friends, now it's a moment you all been waiting for. High level architecture. So we are back and we will do high level architecture now. Why we are back? Because I took some time in between recording this video to kind of get something, remove my previous things which we talked about, like post, API, and all those things, and kind of go on a high level architecture flow with you. So now how I am going to make this is now there will not be a lot of words. So there will be only few things and that's what we are going to do here. But give me some time so we will be able to give you a proper thing. So let's just go with it, okay? Um, we will consist this on 5 layer, okay? So the first thing will be a client layer, and then it will be a API gateway authentication layer, and then it will be the core services, okay, and then it will be data layer, and then it will be like external partners. Don't worry, this is not the actual thing. So how does it looks like? Right now, it looks just uh, a small design, right? Without nothing, without anything into picture. So let us now build. So what did I mention here? Let's just go with this. So first is like a tier one. It is a client layer. You don't have to worry about it. We'll just design. But for now, let's talk about this. So what you will have? You will have mobile app. Okay, you will have a mobile app. You can have a web single page applications. You can have uh, merchant SDKs. That's a good thing. You can have OAuth clients, right? Now, come back to tier two. Tier two. It's like gateway plus authentication, right? So here, what you will have? You will have like authentication. That means API gateway. This will be responsible for rate limiting, routing, and all those things. You will have then auth service, which is like JWT and OAuth, and then you will have the TTS and DDoS shield. That means you will decrypt and all those things. Now let us come back to the code. So what you will have a payment orchestrator here, right? Let me move this little bit. Okay, you will have a payment orchestrator. That can be good. Okay. Then you will have the wallet services. This will be in charge of your balances and holds. You will have a ledger service. You will also have a fraud detection engine. What it will do, it will have rules and asynchronous ML things. You will have a forex exchange service for rates and conversion. You will have a notification service, and you will have the KYC services. Good thing. Now what you will have? You will have the third layer completed, then you will have a data layer. Right, data layer, you will have PostgreSDB for what? This will be for your wallet, for your users, for your ledger, wherever you require atomicity. You will have Redis. Redis will have sessions and idempotency. You will have Kafka for event buses, the whole append only thing. And then you will have Elastic for text search. Then you will come to the last part of it, which is not much crucial. You can just keep it like this, but you can have external processors, right? What, like Stripe, Iden, I think Charge B2. You can have like uh, you can have bank rails like SEPA, Swift, and all those things. You can have KYC providers. You can have the communications like Twilio, FCM, and all those things. Okay, so let's just simply go and understand what I am trying to build here. So we need to go with this route, like client will talk to this one, and this guy will talk, or tier 2 will talk to this one, and here the authentication service will issue two tokens, right? What two tokens? One is a short-lived JWT token for API calls, and a refresh token for 7 days, so that you can have a refresh, and it will be stored in your HTTP only cookie. So whenever this JWT expires, the client silently refresh using the refresh token. So that means the user will automatically stays logged in. Now let us talk to what is this, man? Okay, let us talk to the core services. Like, the user service is there, which will manage like KYC state. It will manage the user profiles and all those things. Then you will have a KYC service. It will manage the integrate with the providers like I we talked about Jumio, Onfido, or for identity verification, and it will async results back via a webhook. Now this wallet service will be the source of truth for all the wallets. It will handle the fund reservation and release. There is a payment orchestrator. It is the brain. It will coordinate between the payment saga across fraud, ledger, and like external processors and all those things. Now, ledger will be like append only, double entry bookkeeping. It will never update. It will never delete. Fraud engine will have fast rule-based checks. It will be synchronously, and then there will be a async ML scoring for enrichment. Forex, where will you have the fetch the live rates and everything, and then you will have the notification system where you will have Kafka and all those things. So the payment orchestrator is the most complex and it's a saga coordinator. So it's responsible here for making a multi-step process either fully succeeds or fully compensated. Now, we already talked about Postgres and we talked about the external payment partners, right? So now let's go to a bigger one and see what we can actually do. Okay. So by what do I mean by this? I mean by this is like how your system will actually work. So think about like this on a very simple chance, like your end-to-end flow, how it will work. So see your client, like this is your client, okay, and your client will what? Okay, this is wrong. Escape, escape. Uh, you will delete it and then you go to it. Your client will talk to your API gateway. Your API gateway will, okay, so let me just, your API gateway will talk to your payment processor. Okay, your payment processor will have another check and then it will talk to your wallet service. And before that, it will talk to your fraud engine. Then it will talk, the wallet service will talk to your ledger service. And then it will talk to your payment processor. And then it will talk to your wallet plus ledger service again, and then it will go to Kafka, and then finally it will go to notification. So let me give you one more time what is the problem. So now it's client here, right? So client will say a post request via payments and idempotency key, and it will come to API gateway, right? API gateway will actually do the following thing. What it will do? It will do the validation of the JWT token. It will check if the rate limit is fine, and then it will forward it to the main candidate, which is called the payment orchestrator. Okay, payment orchestrator. So what this guy will do? This guy will actually first go and do a small check. What is this? This is Redis. Okay, not too looking good, Redis. I think, yeah. Okay, here it will check the idempotency key and then it will say if it's fine, it will just return this from here. If not, it will go to the next loop, which it will talk to a fraud engine. Fraud engine will have its own thing. Okay, like if this particular ID is blocked or you need to challenge it. So in this case, it will return it to the caller that this is something which we have detected it flawed. So how we can check it? Check the velocity. It will check the geo location and it will check the device. Velocity means what? Are you sending a lot of transaction in a short span? Are you sending from two different location or blocked location? And are you sending from a different device and via VPN or something like that? Right? If everything is fine from here, it will go and check the wallet service. Okay, so the wallet service will do what? So the wallet service will actually select for the update and it will block the funds. And then it will go and do a ledger entry. Okay, in the ledger service that, yeah, we are good. We have got the fund. We will keep debit pending entry and that's fine. And then what we will do is we will go to something called a main guy, which is a payment processor, that means external payment vendor, and we will send it to them and it will actually now do the same task that it will send us back what is a payment thing, and we will implement this in the wallet and we'll set it in the ledger. At the same point of time we will update this to wallet, right? Now what will happen is the wallet will actually go and do this thing that, hey, Mr. Kafka, this is a Kafka event bus, and we can now submit this that the payment has been processed. And then this guy will actually go and call the notification services, right? And we will just push, and this notification service now will go to client, and this guy will be staying alone. So this is how the another flow will look like. Okay, so how this flow looks, I can explain you one more time. So suppose, let's trace now a single payment. You send $100 to a merchant. From the moment you tap pay, to the moment both parties get their notification. So client now sends, and we go to API gateway, will validate the JWT, it will check the rate limits, and it will route to the payment orchestrator. The first thing the payment orchestrator will do, it will check the Redis if this idempotency key is present. If it present, it will just return the cache response. Okay, what it will do? It will do this, and it will do the same here. So suppose like this. Now, if everything is good, it will the fraud detection will also be called synchronously, and rule-based check will be under 50 milliseconds. Velocity check, like if the user is sending, as I mentioned, geo anomaly, are they logging in from same location or but transacting from a different location. Fingerprint you will check, and you will then output you will say allow, challenge, or block. If there is a challenge, that means we will use a 3ds flow, and we will pause this particular saga event. If block, will just return with 402. If allow, we will continue. Then we will go to the wallet service, right? Here we are coming, and we will update the sender's wallet row, and this is a then we will have a pessimistic lock. That means no other transaction can now modify it, and we will deduct the 100 PLM from the available balance, and then the 100 PLM will be added to the pending balance. All this will be inside 1 DB transaction. So if any step will fail, we will release the hold. Now, once it is done, we will do a ledger service, which will write a debit pending entry. That means double entry bookkeeping. Means what? One debit row for the sender, one credit row for the receiver, both with the status pending. Okay. Then what will happen? Then the external processor, payment processor will be called. And if it's a wallet to wallet, this payment processor will be skipped entirely. If it's a card payment, we will call the orchestrator, we'll call Stripe, and we will have the tokenized card details and the amount. Stripe will call the card network, get an authorization code, return authorized, decline, timeout, then orchestrator will wait, retry once again with the exponential back off. Okay, so this all things will happen. Now let's talk about settlement. Now your wallet service says, or your card says everything is good. So now your sender will hold the pending balance back to zero. It will credit the $100 to the receiver bank account in the available balance. Ledger will now update both rows to completed. That means there will be a different thing, not the same thing. Notification service will pick up the event, send push notification to the sender, right? And then you will send, now the both things will get, you will get, you sent 100 pln to sender, and they will get, you received 100 pln from you. Both will be done under 500 milliseconds for settlement. So notice that what we never done, we have never move money at the application layer without matching a ledger entry. So that means the ledger, right, ledger and the wallet will always be in sync. If you want to know any wallet's true balance, you can replay ledger from scratch and arrive at the same number. That is your audit trail, your forensic tool, and your source of truth, right? Now there is another one where we talk about like how it happens, but this is how it will look like. But if you want to talk about something else, uh, I have another thing which you can do. So, is something which we want to talk about in the deep dive. And let us first see what I have for you in the deep dive. I have a small, good enough created I think image for you, because this image is maybe a bad one for you. So let us try to see if I can bring that image into here. Yeah, look. It's here. So now the main part of this is uh, saga design pattern. Okay, you will say, okay, why are we moving here? We should not, but it is very important. So we have now got a full picture what is going to happen, and now we will go deep into four problems that will actually make or break a payment system. Like distributed transaction management, we will check fraud detection, we will check multi-currency forex, and then we will check the ledger design. So let's just talk about Saga pattern for distributed transaction. So here's the problem. Your payment is actually touching minimum or four services. That means a wallet service, a fraud engine, a ledger service, and a forex exchange. Okay. Suppose your step succeeds at 3 but fails at 4. Now you have a partial state. That means money is reserved, ledger entry exists, but the payment is not completed. So a native or a naive solution would have been a two-phase commit where you have taken a lock across all the services, and if suppose anything goes back, the lock has been not been done, so you'll not do anything, right? But the two-phase commit has a very large problem in microservices. It's blocking, it's synchronous, it's slow. So if and also it depends on the coordinator. So if a coordinator crashes during the commit phase, you can now can hold the lock forever, right? So it's not viable for a 10,000 transactions per second. So a real solution is you need to draw a orchestration layer where you will go from fraud to wallet to ledger to forex. So this is how the payment orchestrator is working. Now there are two flavors of Saga. One is choreography and one is orchestration. So choreography is like everyone is independent. They all do the work and then they publish the event. The next service will take that event and reacts. It's fully decoupled. But if something goes wrong, it's very hard to trace on what happened, right? You need to check the append only log, check one wet, and do all the things. But in an orchestration, it almost like a two-phase commit, but asynchronous. So there's a central orchestrator which explicitly commands each step, like way we have it here, and it knows the full state of the payment at every moment. So whenever the step 3 fails, it knows that this has failed, so it will call the compensating transaction. Now, what is compensating transaction? It's not DB rollback. It's like the undo plan. So every forward step has a defined compensation. Like reserve funds will have a compensation release hold. Debit pending to ledger write compensation is a write reversal entry. Call external processor will have a compensation is like issue void authorization, and the credit receiver will have a compensation of debit receiver back. So this orchestrator is persist in its saga state to the database at every step. If it crashes and mid payment and restart, I mean, so basically they will ask you like, if what if the orchestrator fails, what you will do? So basically, this will orchestrator will actually persist the state in a database every step. Anything goes bad in mid payment and it restart, it will check the saved state, pick up from where it left off, so that the saga step is idempotent. So that means you will running every same step twice produces the same results. So what if the interviewer asks, what happens if the orchestrator itself fails? So that's the answer we have given. You will persist the saga step, you will have idempotent step, the orchestrator can always recover. So now let's go more into a fraud engine. So fraud engine will have two layers right here. One layer is a real-time rule engine which will give you the result in 50 milliseconds. And this will be having what? So this will be having it will run synchronously. It will have a evaluated in-memory model. We will use Redis for fast lookup, and we will have like rule engine like rules for the logic. It will check the velocity if the user has made more than 5 payments in the last 60 seconds. It will check a amount threshold for the user, like suppose first transaction should not be more and all those things. It will have a geo impossibility, like he is logging from US but doing the payment from India in 3 minutes later. So that means physically impossible. Device fingerprint is also checked. It also check the card bin country versus billing address if the country is mismatched. It can also check merchant risk category like it's a gambling, cryptography, or adult content have higher baseline fraud rates, right? So those things can be done. Now there is an output in three-way decision. That means it's a allow or either it's a challenge. So once there is a challenge, it will trigger the 3D secure or SMS OTP, or it will simply block. The rule engine will take this in 50 milliseconds and the user will not notice it. Second is this. It is like a after this payment is completed or suppose it's challenged, we will enrich it with a ML generated risk score and it will run asynchronously. It will not block the payment. So what can we do? We can have a transaction graph like who has this user paid before. First time pay is a higher risk. We can have behavioral biometrics like typing speed, scrolling pattern, device tilt, those things, right? Historical chargeback rate also we can check. Time of the day we can also check. Suppose like user never transacted 3 a.m. Why it is doing it now? So that ML score is stored on the transaction record. High scores go into a human review, right? Queue, and the fraud ops team reviews this and all those things. And if it's a confirmed fraud or a false positive, these are the labels that will go back to the model training loop so that it gets smarter over time. We can also do this like if you have a new model, we can actually append it, but not send this thing to the noodles. I am saying users, right? Um, this is done. Now let's go to deep dive for multi-currency and forex exchange. This multi-currency sounds so simple, but it's not like this. So you first rule is never use float or double, right? You will always use like big decimal in Java, numeric in Postgres, or decimal in Python, but never use float. Second is like snapshot and log the forex rate. So forex rate it's like changes every second. So suppose if I show you that you will pay 23.45 USD at checkout and the rate changes before you tap confirm, you get a different rate. That's a terrible experience. Solution is that forex service will fetch a rate from a provider every 60 seconds and it will cache them in Redis. And when you enter the checkout, the snapshot the current rate and lock it for 15 minutes. So even if you don't complete the checkout in 50 minutes, the rate refreshes. Okay. So critically, we store the exact forex rate alongside every ledger entry. So you will need this when you will do the reconciliation. So what are things we have done? That you will not do instant forex rate. You will take a 60-second provider. You will take that snapshot. Once you go into the checkout phase, you will block it for 15 minutes, and then if suppose even after 15 minutes you are not able to do the transactions, then only you will go and refresh the rate. Also, every forex rate, whenever you do, you also have to like add this in your ledger entry so that they know what is going on. The platform forex account. So suppose I sent 100 USD and the merchant received 25, suppose uh, around 1,000 INR. The amount doesn't perfectly balance because the risk spread the platform charges, right? So how do you keep the ledger balance? So you create a platform forex revenue account, and like the debit side is like 100 USD from my side, the credit side is like 10,000 INR to merchant, plus a credit of the spread to the forex account in whatever currency you want to do. So what does it means by that? The ledger stays balanced in every currency independently. So if a merchant has INR, they will get the INR currency, and I will get the forex revenue of USD one. Got it? Now let's come to ledger. So for ledger, we will have a double entry ledger. So what will be the ledger having to us? So if you see the ledger will have a ID, it will be a UUID, it will have a transaction. So it will have a UUID, it will have a transaction, it will also be of a UUID, it will have a wallet ID, again a UUID, entry type, right? It will be a enum, it will be a amount, same currency, status. Let's go back up. Created at item potency, metadata. So see, so many things are there. Now the thing is, there is no update, right? There is no update, no delete, as we mentioned. Every reversal will have a new thing as reverse. Even reversal will have a reverse status. So every refund is a new row with type credit. That means you have credited it and someone has to debit it, right? You can always reconstruct the wallet balance at any point in history by summing the ledger rows where wallet ID matches and created. So, therefore, before your target time is 10, you can do all these things. This is how you can do the reconciliation. At the end of the day, you will check the sum of the all completed ledger entries. You will compare them with the bank settlement fee. So, what you will do, end of the day, completed ledger entries you need to compare with what? With the bank settlement files. If any mismatch, you will trigger the payment ops team. Okay, so this is how we have designed the system. If you look like it doesn't look much, but this is how you can design the system. You don't need to design everything like that. So, like we have built a whole big payment system from scratch. So, what are the five things now which you can remember? Absolutely remember. Is the first thing is you need to talk about, let us write it down as well. You need to talk about consistency over availability, right? Say it out loud. Money demands acid. What is this? Money demands acid, not the acid which you are thinking, not eventual consistency. So that means every interviewer at a fintech, if it's a Razorpay, Stripe, Voice, Revolut, will probe this. If you default to eventual consistency for scalability, you are out. Second is idempotency everywhere. You have seen this, right? UUID, everything is idempotent. So you need to keep it. Every payment endpoint, every webhook handler, idempotency key header should be there. Check Redis before processing. Return the cache response if it's a duplicate. There is a difference between the system that handles retry gracefully and the one that bankrupts the user. Now, third is saga pattern for distributed transactions. So you need to use orchestration here, not choreography. I have also designed a proper all these things into a complete different video. You can find it here, or maybe in the end of the channel because you are right now till here. So you can take care of all these things. Then you go with two-layer fraud. That means the fast rules in the hot path, async ML in the less path, because the hot path should be under 100 milliseconds so that you can just check. And then the last one is append only ledger. Never update. Anything happens, it should be a single flow so that you can reconcile, right? And if you're heading for the interview, practice drawing the full architecture from memory in under 10 minutes. Draw the 5 tiers we talked about, and then narrate the payment flow, state the NFR trade-offs. That's the real test. And if you follow and if you found this video useful, drop a like. It's genuinely helped the video reach more engineers preparing for the interview. Subscribe if you want the full series. We have got distributed rate limiter, ride sharing, notification, everything coming through. And drop a comment with your company you're interviewing for, and I might tell you what angle they care about the most. I generally read all the comments, and that's it. All right, that's a wrap. See you in the next one. It's been a long run. Thank you. Take care.